Okay guys, in this video segment we're going to be talking about standard heats of formation and how we can use the individual heats of formation of compounds to actually combine them together to solve for the heat of a reaction. So if you recall, we talked about heats of reaction in our last video, and we were just using this number that was given to us. So in this video segment, what we're going to do is talk about how we actually can calculate this number or determine this number from the components or the individual pieces of a chemical reaction. So to do that, we need to get a better idea of what a standard heat of formation really is. Okay. So when a substance is created from its components, okay, so when we're actually making something from its most elemental steps, we actually can determine the energy change for that substance. So for example, if I was going to take hydrogen gas, react that with oxygen gas, and make water as a gas, this process, okay, hydrogen is in its natural state, meaning that it always comes as a diatomic. It comes as a gas in our standard conditions. Oxygen is in its natural state. It's a diatomic as a gas in its natural conditions. So these two substances don't take any energy to form them because they're naturally that way. However, water is a compound. So it's not in its elemental or natural state. We've actually had to combine hydrogen with oxygen to make water. So if we wanted to know how much energy it takes to make water, we can actually calculate that or pull that number up off of an actual table or a data table for us. In this case, to make water, we actually release 241.8 kilojoules per mole. So the heat of formation for water is this number. Okay. Now, once we know that, anytime we see water in its gaseous state in a chemical equation, we know that if we're making water, it's going to release this much energy. We also know if we're breaking water apart, it's going to absorb that much energy. Now, imagine doing that with multiple compounds. You actually can start adding up all the different pieces of a chemical reaction. But it comes from, how do you make a compound from its elemental or its diatomic pieces of that? Okay. So what we have, a couple of things we need to talk about. We need to be in standard conditions because these numbers would change if we change the temperature or change pressure. So we're going to standardize our conditions at 25 degrees Celsius and 1 atmosphere pressure. The symbolism we use for standard heat of formation is your delta H. This is a little knot symbol. Okay, that stands for standardized. So it's your standard H, it's your enthalpy standardized. F for formation. Okay, not to be confused with fusion, which we've used before, but the little knot symbol helps you with that. Our label here is going to be in kilojoules per mole. And then once we know these independent numbers for every element, we can use them to calculate the entire heat of a reaction from every substance within that. So what we want to do is talk about one of these numbers positive, one of these numbers negative, and what's that mean to us. Okay? So when you are absorbing energy, so if you take a look at this kind of graphic, we have a plane here. The plane represents 0, HF being 0. So your elements and your diatomics are going to sit on the plane. Notice how the diatomics, they're in their natural state. So oxygen is a gas, hydrogen is a gas, nitrogen is a gas. If you had oxygen as a liquid, it would not be 0. It would either have absorbed energy or released some energy to make it into its liquid form. Because oxygen doesn't come as a liquid typically in our conditions. It comes as a gas. Same thing for any other element that's up here. Anything in brown, they had to absorb energy to make them. Okay, so if they're absorbing energy, that's an endothermic kind of process. What it also tells us is that when you absorb these substances, that they're less stable. So we have something like acetylene up here, C2H2. It absorbed a lot of energy to make it, which means now those bonds that acetylene has carry a lot of potential energy, which makes it a less stable substance. However, substances down here that all have negative enthalpies of formation, these become more stable as you make them. So carbon dioxide and water are more stable type compounds. Okay, so when you create water, it releases energy when it's formed. When you create acetylene, it actually absorbs energy to be formed. Okay, now one thing to make sure that we keep in mind, all free elements, free meaning just straight from the periodic table in their natural state, and diatomics, also in their correct state of matter, have a heat of fusion or heat of formation of 0 kilojoules per mole. Okay. Now, one thing we want to make a note of: if you're going to form these are called heats of formation, so it's going to absorb energy. So what would happen if you actually broke it apart? Okay. So for example, when you react acetylene, it's not forming. Let's say we do a combustion reaction with acetylene. So if acetylene is a reactant right here, it's not a product. We're not making acetylene, we're actually separating it. Okay? So when it acts as a reactant, we're not forming these, we're separating them. So if it's a positive number to form them, we could probably assume that if you actually were to separate them, it would turn to a negative number. Okay? So for things like acetylene, they're going to be negative, or they're going to release energy when they're separated. Same thing for the substances up here. When you form carbon dioxide, it was negative. So if you're going to separate that, or you're going to try to break carbon dioxide apart, it's going to absorb a lot of energy to make that happen, which tells you it's really hard to separate water. It's hard to separate carbon dioxide because you need a lot of energy to do it because they're more stable. Acetylene, however, really easy to actually break it apart because it's less stable as a compound, and it actually wants to break apart to release this extra energy that it has. Okay. Now, working with this process, we need a formula. Okay. So here's our basic equation. A little squiggly e here. Okay. Actually stands for the sum of. Okay. So it's a Greek letter sigma, and it stands for the sum of your stuff. So we have the sum of our heats of formation for our products minus the sum of the heats of formation for our reactants. Okay, so you take your products minus your reactants. We say it's a sum because you may have 2 or 3 products, so you want to add them all together, and you may have 2 or 3 reactants, you want to add them all together. We also put a negative sign in here because the heat of reaction has to not form everything. It only forms your products, it separates your reactants. So by putting a negative sign in our equation, what we're essentially doing is we're actually taking those heats of formation and we're flipping their sign by giving them a negative value. So we can run the equation and pull normal heats of formation numbers out for all these substances. So let's do a quick one here together. So we have sodium chloride, and it's going to react to just separate into sodium ions and chlorine ions. Okay, so this is actually this reaction is actually a dissolving process or a heat of solution process. Okay, so what we need is we need to know the heat of formation for sodium chloride, the heat of formation for sodium ions, and the heat of formation for our chlorine ions. Okay, so let's list out what we need and solve the problem. Okay, so to solve this, we need to know the heat for formations for these 3 substances. Okay, so to do that, we have to look up this information, and we can find these on different data tables as we look them up. Now, in your notes or also in this presentation, we have some of those values. So if we take a look at this table, this gives you standard heats of formation for a lot of different compounds. And if you notice that there isn't any of these things on this table. So if we go to this one, now we're looking for those standard heats values again, and I don't see any of those on this one either. Okay, so let's go to the next one. So we have another table of standardized values. And here we have sodium ions are negative 240.1. So the heat of formation for sodium ions is a negative 240.1 kilojoules per mole. For chlorine ions, it's a negative 67.2 kilojoules per mole. Okay, so we know our 2 products, however, we still don't know our reactant. So if you can't find it on a standard table like these that I give you, you may actually have to go out and do a research or a search for that. So if we go to the web and we say enthalpy of formation for NaCl, okay, standard change of formation data table on Wikipedia. Let's try it. Okay. So it gives us all sorts of different values here. And we're looking for sodium. So here's calcium, water, iodine, iron, magnesium, ammonia, nickel, potassium, sodium. So sodium chloride, here we have, and we have it as in solution, as a solid, as a liquid, as a gas. So in this case, we have a solid, so we look over, it's a negative 411.12. So sodium chloride is a negative 411.12 kilojoules per mole. Okay, so most of our common compounds, if you take a look, we have a lot of data on that already that's been researched and studied and then presented for us to use. So if you're doing this, you could really look up most of these individual values, even if I don't provide them on a table for you. Okay, so if we go back to our original problem here, we want to solve for this now. So we need to take the sum of our products minus the sum of our reactants. So our products are here. So I'm going to take a negative 240.1 kilojoules per mole. And in my balanced equation, I have 1 mole of sodium chloride, 1 mole of sodium, and 1 mole of chlorine. So we want to get rid of the moles, so we're going to take these times the number of moles we have. Now in this case they're all ones, so it's easy, but in other practice examples we may not have all ones. So take that number times 1 mole of sodium ions. That is going to be added to our chlorine, which is a negative 167.2 kilojoules per mole, times 1 mole of the chlorine. And then these two values, we're going to subtract away the sodium chloride. So we're going to subtract the negative 411.12 kilojoules per mole. Take that times 1 mole of sodium chloride. Okay. Now essentially we're subtracting the reactant, again, because we don't want the formation of the reactant, we want the separation of the reactants. So by subtracting that, we're essentially factoring that into our equation. Okay? So if you plug all these numbers in, we get an equation that looks like this on our screen. So we have our sodium, we have our chlorine, we have the number of moles of each one of those, we have our sodium chloride, its moles, and we put the math in, and we get 3.82 kilojoules. Okay? So the heat of reaction for this process is 3.82 kilojoules. Okay? It's a positive number, so being a positive number, it tells you that this reaction is actually endothermic, which means it's going to get cold as you dissolve this stuff. Okay? Now, we've seen these tables. Here's one for you guys to try. What's the standard heat of reaction for the combustion of acetylene? Okay? So let's set up the combustion equation and we'll let you guys solve it. So acetylene is C2H2. And we're going to combust it in oxygen as a gas. We're going to make carbon dioxide gas and water as a gas. Okay? So here's your basic setup. First step, you got to balance it. So you know what your values are. Okay? And then you need to look up the individual heats of formation for each one of these. So if we go back to our tables, we should be able to find those all on this particular table. So if we look, here is acetylene. So its heat of formation is 226.7. Oxygen is not on this table. Okay? Is that a problem? Oh wait, it's not a problem because oxygen is a natural state as a diatomic, as a gas. So oxygen's heat is a 0. So that one we don't need to worry about. We're going to make water. We either can do it as a gas or as a liquid, and we roll it up as a gas. So water is a gas, so it's a negative 241.8 kilojoules per mole. And here's carbon dioxide at a negative 393.5 kilojoules per mole. So we have all the numbers that we need in our process. You have to balance it, put it into your equation, and then go ahead and solve. Okay? So I'll give you a minute to work on that, and then we'll come back and show you the answer to it. Okay, so here's our acetylene example, and if we pull up the actual answer key here, first thing we want to make sure we do is we balanced it correctly. So we have a 2 to 5 to 4 to 2 ratio. making sure that you use these coefficients in your equation. And if we put it together, we end up using our carbon dioxide times its 4. We have our gaseous water times its 2 moles. Subtracting the acetylene times its 2 moles, and so adding that to the 5 moles of oxygen, which is a 0 because it's in its natural state. If we put those together, we get a negative 2,511 kilojoules of energy. Now, if you were to put this into an actual thermochemical equation, we'd write it in line. Because it was negative, it'd be a product, and we'd write it as 2,511 kilojoules here. If we wrote it as a separate entity, we would put it in our equation and write the heat of reaction standardized is a negative 2,511 kilojoules for our process here. Okay, we're going to end the video here. Thank you.